Okay, so continuing on, what I want to do is talk a little bit about some of the millennial scale climate changes that have happened within these glacial cycles. And so even within these bigger periods of glaciations and interglacial periods, we see some minor climate change here and there. And there are a few in particular that I want to mention. Some of these you may or may not have heard about before, but the Younger Dryas, that is something that is occasionally will just kind of come up in not really popular culture, but sometimes you will see it on websites, or you'll see people talk about hypotheses for what caused this change in climate variation. So you may have heard that word before just because it comes up in that way. But the Younger Dryas was a very abrupt cold snap that occurred at the end of the last glacial cycle. So as we were warming up, as you can see here, warming up out of the last glaciation, and then boom, we had this period called the Younger Dryas that was about 1,300 to 2,000 years or so total of colder than normal temperatures. We'll talk perhaps about why that may have happened, but it's something that we don't really understand exceptionally well. A couple others more recent, the medieval warming period, which was from about 800 to 1200 AD, right? So Common Era, AD, same thing. And then the Little Ice Age which was Common Era, or AD 1600 to 1850. And so this was even more recent. So the medieval warming period, as you can see here on this particular diagram in terms of when that took place, corresponds to a period of the colonialization of North America. It doesn't make sense, of course, that there would be any kind of correlation between the two, but it is an interesting thing that happened during that particular period. The weather, or I shouldn't say weather, sorry, that's not the right word at all, but the climate in general was about 1 degree to a half degree warmer than what the average was then for the 20th century. So it's a little bit warmer than typical. We know this because we have historical accounts of this particular period. Of course, people were around and writing by this time. And so, for example, there are historical accounts of like growing figs and pomegranates and olives in the Rhine Valley of Germany. And if we think about what the Rhine Valley of Germany is like today, it's a much cooler region. And so not a place where we can grow those kinds of warmer fruits and vegetables and things. The Little Ice Age was certainly much more recent, and it was about a little less than 1 degree cooler than the average for the 20th century. And so that's very, very modern. We have a lot of written evidence of this as well. And we also can look at historical images to understand that this has happened. The image here on the left is a drawing, so not a picture, but a drawing from 1850, right? And this is a glacier valley in the French Alps. So you can see at that particular time, that valley was filled with a very large glacier, which was coming down right onto the edge of the city. Very unusual, right? So cooler than typical. And here's a photograph of that same valley. You can actually see the little church here, get an idea of like your reference point. That was taken in 1966, and of course that glacier is completely gone even in the 60s, so that's not necessarily just a modern thing. That's just a fact of, or a result of the fact that we had a warming after the Little Ice Age from about 1600 to 1850. So that is an interesting thing. So in addition to writings and paintings, how else do we understand these more modern climate change? So in addition to things like oxygen isotopes, what else can we use? One of the ways that we construct really recent climate is using tree rings. Of course, tree rings only go back to the age of the forest, and so that's going to limit when or the extent that we can use this particular method. But what do we know about tree rings? Well, we know that they grow slowly during cool years and they grow more quickly during warm years. And so there's always a record of growth in the tree, and those are the individual rings. And there's a whole area of science called dendrochronology, which is using tree rings to date things. And so each ring corresponds to a year of growth, and we can see rainy seasons, we can see dry seasons. This even illustrates a scar from a forest fire. So when the tree was this thickness, when that was the edge of the tree, there was some kind of fire, and that is recorded in the growth rings of the tree. We can compare tree rings to instrumental measurements for more modern day time just to see how accurate they are. And this is actually what's been done in this figure here at the bottom. So the instrumental measurements are in red, and the tree ring reconstructions, which means that the temperatures that we get from the tree rings, are shown here in black. And so you can see there's a pretty strong correlation between the two. The exact temperatures don't necessarily always match, but what we do see is the pattern is the same. So we can certainly see the changes, the fluctuations in the temperature over time using tree rings. So we can use that as a way to look at modern or more recent climate change. Pollen works in the same way, or microfossils, but typically when we think of microfossils, we think primarily of fossils of pollen. And that's because vegetation also changes during changes in temperature, right? Certain plants grow in certain temperate conditions, right, or certain temperature conditions, I should say. Like if I just think about, comparing how it was when we lived in Illinois to how it is when we live in, or now that we live in Maine, is a very, very different way that we plant in the summer now, because it's much cooler in Maine than it was in Illinois. And so in Illinois, we could start planting, let's say, tomatoes a whole month earlier than we can in Maine, because Maine is just still too cold. And so we have a much smaller or shorter growing season here in Maine because of the weather, because of the temperature. And so like here's just an example of how we might distinguish between spruce pollen and grass pollen. And grass pollen is a type of pollen that dominates when it's warmer, and spruce is a type of pollen that dominates when it's colder. And so again, we can take look at the sedimentary record, right? Take a core into the sediment, look at that sediment core and see when is spruce pollen dominating the core and when is grass pollen dominating the core. And this here actually goes back to, probably about 90,000 years or so. So recent at the top, 90,000 years ago at the bottom, just to illustrate how that has changed over time. And so you can see in the last 10,000 years, we've actually, wherever this particular column was taken from was dominated by spruce, whereas it had some periods of grass and then spruce and grass and spruce. And so you can see that change over time, that change in the vegetation, which then also can indicate to us that we've had a change in the temperature as well. Now we might say, well, how do we know that that's not a change in temperature due to like location of continents, right? Because we talked about the fact that continents move around. Remember, the time scales are different, and we also know that continents haven't moved within the last 100,000 years. Like that was a more older move than a recent move. And so there's been no change in the position of the continents. So what has to have change in this area is the overall climate. Another way that we can understand short-term climate change and think about what is causing this is ocean circulation. And we talked briefly about that in the last lecture, and I said I would come back to that and talk about that in more detail. What we learned in the last lecture is that the ocean circulation has to move around continents. Like you can't circulate water through continents, obviously. It's like stuff that's in the way, so you have to go around the landmass. And so this is a simplified version of what the overall global circulation of the Earth looks like. Areas that are red, of course, are areas where it's primarily hot water. Areas that are blue are areas where it's colder water. And so the darker the blue, the colder it is. And so you can see that the coldest water is down here near Antarctica. So that's the deep, cold ocean circulation, ocean water. And what happens to that water is that as it moves up, right, into the northern hemisphere, right, moves up towards the equator. When it gets to the equator, it starts to warm up significantly, right, because it is very hot at the equator. And that heat is actually able to be carried and transported all the way up. This is what we call the Gulf Stream. So the Gulf Stream transport this all the way up between North America and Europe, up to Greenland and up to the northern Atlantic. When it reaches the northern Atlantic, what happens is that all of that heat is released, right, because that water starts to cool down. So that cold water sinks back down and moves back down towards the equator, and you can see kind of goes back into that cycle again. And this is what we call thermohaline ocean circulation. Thermohaline is a fancy word for hot water, hot salty water, basically, because the things that are driving ocean circulation on Earth are heat. That's working in the same way that that density works when we're heating up water on a stove, right? Remember we talked about that kind of convection, right? So this is basically kind of a convection. And so the water that is deep is colder. When it rises, or when it is heated up, like when it gets to the equator, it is heated up, and so that heat rises to the surface. That heat eventually dissipates at the northern end of this, and then the cold water sinks back down. And so it's kind of a density-driven circulation. But salt is also important here too. Deeper water, colder water tends to be saltier, and warmer water towards the surface tends to be less salty. And so it's the heat and the salt that is driving the thermohaline circulation. And that explains why we can have such different, what we would call weather, in places that are the same latitude. And so here's an example. This is Churchill, Manitoba, and this is Glasgow, Scotland, which are at roughly the same latitude, so, position on the Earth. But if we look at the general climate of both of those areas, what we see is that Manitoba, right in this part of Canada, is very cold all year round. Now, there are certainly seasons like summer where it is warmer in Manitoba, but it tends to be a very cold place all the time. You can see the little polar bear walking around, indicating that's very, very icy and very cold. Whereas if we look at Glasgow, never looks like this, right? It's never cold like that in Europe in the way that it is in North America. And it is the Gulf Stream that is responsible for that, right? If we look at where the heat is pulled up and it is pulled over here closer to the UK, right, to the United Kingdom and Europe. So all of the heat from the Gulf Stream is keeping Europe hotter or warmer year round. And we look at what happens to that as it comes back down towards North America, then it is bringing colder air down. So taking warm air up to Europe and bringing cold air down to North America. And so that is why we have differences in climate, even in places we might assume to have similar climates because of where they are located in terms of latitude. So ocean circulation is really important. Now, another thing about this is that thermohaline circulation, like this is the circulation that's really driving heat movement and water across the globe. If it was to slow down or to stop, this would be problematic. One of the reasons it would be problematic, in addition to the fact that it would change the way that heat is moved around the planet, is it would also change the way that oxygen is moved in the oceans. Oxygen tends to be carried in that deep, cold ocean water, and so which again is always moving around the planet. If you stop thermohaline circulation, then you stop the circulation, the movement of that cold, oxygen-rich water. And so that would be problematic, of course, in that things in the ocean would begin to die because of the lack of oxygen. And we are concerned that we're actually starting to see a stagnation in the thermohaline circulation, or a slowing down of the thermohaline circulation. And if you start to lose oxygen in the water, then organisms start to die in the water, then that's going to have, of course, a bigger effect globally on the food cycle. So that's always a big problem. So what will cause thermohaline circulation to stop? A couple of things. Well, the first thing that can cause thermohaline circulation to stop globally is if you have a global increase in temperature. So if the planet is generally warmer, let's say then, for example, than it is right now, so much, much hotter than it would be in modern time, then that means that the North Pole and the South Pole are not going to be cold in the same way that they are today. And so if you don't have the coolness, right, if you don't have that cold part of thermohaline circulation, then it's just hot water all the time. And so it's not going to circulate, right? You're not going to have a density-driven circulation if your water is one temperature. And so oxygen stops, right? Everything gets hotter, everything starts to die. We think this is a potential source of the Permian extinction, and the Permian extinction is the biggest extinction in all geologic history. Most people think of it as the dinosaur extinction at the KT boundary, but that is not the case. The Permian extinction, as far as we can tell, we think killed somewhere between 85 to 95% of land animals and ocean animals, and that number was higher in the oceans than it was on the land because, again, it was an ocean-based type of extinction. And so a pause or a stop in the thermohaline circulation is one of the explanations for this extinction event, and it would have been because the planet was much warmer. A decrease in salinity can also stop thermohaline circulation, and this has been proposed for as one possible cause of the Younger Dryas, right, which is again a very short climate change. And so we're not necessarily sure about this, but some people have suggested that it's a change in the salinity. What happened, at the end of before the Younger Dryas, as we were coming out of that glacial period, the ice was melting. When ice melts, it puts fresh water into the oceans. If you put fresh water into the oceans, that decreases the salinity, and if you decrease salinity, it perhaps may stop that ocean conveyor belt. Now, I'm not sure how I feel about this necessarily. I'm certainly not a climatologist, and this is not my area of expertise, but this is a thing that would have happened all the time, right? As we come in and out of these glacial cycles, you would certainly see ice melting, fresh water going into the oceans, but we don't see the Younger Dryas at any other time. And so I'm not necessarily sure I think that is the correct explanation for what caused the Younger Dryas. Again, it's a thing we don't understand very, very well. Uh, but certainly this is a way that you could stop solar thermohaline circulation by putting a lot of fresh water very quickly into the oceans and increasing the overall salinity. So that has brought us to the end of our discussion of intermediate and short-term, I always want to say short-term climate variations. So I'll post all these lectures for you, and we will have one more lecture or set of lectures to go with modern climate change. So I will see you for lecture 4.4.